Assessing emotions during interactions is arguably one of the most essential social skills that humans have. And in order to assess other people's emotions, we utilize not just information from multiple senses such as hearing, vision, but also from internal states that we carry and presume others to carry based on previous interactions. Not surprisingly, enabling machines to be able to recognize emotions in conversations finds a large number of commercial applications like marketing and management, user interaction, finance, politics, health, and education. To date, many models attempted to address the problem of emotion recognition in conversations. However, the state-of-the-art performance is still low at around 67%. The template chosen for this project was deep learning on a public dataset. And the dataset chosen was the MELD dataset, a multimodal multi-party dataset for emotion recognition in conversations published by Poria et al. In 2019 that extended the previously existing emotion lines. The MELD dataset adds a sentiment polarity label on top of the emotion lines dataset and also delivers a significant quality improvement with a place kappa score of 0.43. 3 research papers were added to our critique of previous work. The first piece analyzed was the research paper Dialogue RNN by Mujander et al. From 2019. Its proposed model architecture is based on multiple gated recurring units, or GRUs, assembled together to model each speaker's context, as well as the dialogue's context, and use these combined representations as an input to the emotion GRU, responsible for outputting the emotion class. This model leverages the 3 modalities of the input, text, audio, and video. It also leverages the speaker's context as well as the dialogue's context. However, GRUs are limited in terms of CPU-level data parallelization due to their recursive nature. They also paid more attention to recent interactions instead of long-range dependencies, which led to some classification mistakes. The second paper analyzed was the SPCL from 2022, where Song et al. Introduced a contrastive loss function and used it to fine-tune the SIM-CSE model in an attempt to build an embedding space that increases distance between contrastive sentence representations as much as possible. Also, curriculum learning was used to ensure that each mini-batch would have enough positive and negative examples of each class, regardless the batch size. The SPCL algorithm makes use of attention-based representations like Bert and Roberta and improves these representations with this more sophisticated SPCL loss, achieving state-of-the-art results on the MELD benchmark. However, the paper does mention about the multimodal nature of the dataset and the fact that emotions sometimes can only be captured by looking at the different modalities, but leaves this problem unaddressed, only looking at the textual modality. The third paper reviewed was the M2F NET model by Chuda Sama et al. Published in 2022, at present the second best weight F1 score in the MELD benchmark ranking. This paper employs some truly bleeding-edge techniques such as Roberta-based text representations, audio representations trained from MELD features, and even face recognition for videos. Later, it combines and transforms these into a dialogue embedding. An MLP classifier then transforms these representations into an emotion class. M2FNet also leverages the 3 modalities of information, text, audio, and video, addressing the issue left unaddressed by SPCL. However, it does not model speakers individually as Dialogue RNN does. Additionally, this model ensemble is large and relies on a fairly heavy feature extraction process that could potentially be simplified. After taking in consideration the strengths and weaknesses of the models presented by the papers reviewed in the critique of previous work, the present project was laid out. This project aims to perform emotion recognition in conversations, or ERC, on the MELD dataset, and its main objective is to design, train, and evaluate a model both inspired in existing literature, but also assembled in a novel way. The baseline architecture used for this project is inspired in the Dialogue RNN model, with some modifications. Instead of using GRUs to model the speaker and dialogue context, a distilled transformer model like Distill Roberta will be used, in the hope that long-range dependencies will be handled better. Visual information will be restricted to the images of faces, extracted using VGG face or a similar model, rather than feeding information about the scene. A contrastive loss function and curriculum learning will also help the model to structure better its embedding space. Finally, in order to understand how each individual component affects performance, an ablation study will be performed and results will be compared and presented.